ठीक है. अच्छा, so last time I had just told you a little bit about moment of inertia. ठीक है, that if point masses are there, and if point masses, you have to calculate the moment of inertia for a point mass. ठीक है, then how we can calculate? We can calculate it by mr square. And if there is a continuous mass, ठीक है, if there is a continuous mass, we integrate the result of r square dm. ठीक है, that is how we calculated moment of inertia. ठीक है, so let's take it a step further. ठीक है, we had calculated the moment of inertia of a rod, ठीक है, about an axis uh, passing through one of the ends of the rod. ठीक है, one of the ends of the rod. And just as we were finishing the lecture, ठीक है, just as at the end, ठीक है, I said that if you change the axis, ठीक है, if we change the axis, the moment of inertia of the rod also changed. ठीक है, the moment of inertia of the object also changed. ठीक है, so uh, we will see that how that happens. ठीक है, but for now, ठीक है, you have to remember that whenever I change the axis of rotation, ठीक है, whenever I change the axis of rotation, the moment of inertia also changes. ठीक है, it also changes. ठीक है, so let's see a few more calculations. ठीक है, moment of inertia derivations you should know about a few of the shapes, like rod is there, ठीक है, like disc will be there and such. ठीक है, so let's see another calculation you will understand. Yeah, let's see the calculation of the moment of inertia of rod about its center of mass. ठीक है, let's see. Let's prove the point that whenever the axis changes, so no problem. Gravitational potential energy, if you are understanding, then gravitational potential is not required. ठीक है, gravitational potential is the same thing. ठीक है, if you know gravitational potential energy, if you don't know potential, it is not an issue. Not used. ठीक है, you must have seen in the questions that we were using gravitational potential energy only, है ना? So gravitational potential, even if you don't know, ठीक है, it is not an issue, nothing to worry as such. ठीक है, it is basically the same thing. ठीक है, when you again when you have to study again in 12th that electrostatic potential, na? ठीक है, so in that again the concept of gravitational potential will also be covered, you can say. ठीक है, both are the same thing, just one is for electrostatics, one is for charges, other is for masses. ठीक है, so you will get that in later classes, not to worry about that. ठीक है, mute your mic. हाँ, ठीक है, so what we were doing, we had to calculate the moment of inertia of rod when the axis of rotation a dash, ठीक है, when it was passing through the one of the it was passing through the center of mass. ठीक है, suppose the axis of rotation is passing about the center of mass. ठीक है, you can imagine that we are going to rotate the rod about its center. ठीक है, earlier we were rotating the rod about one of its end. ठीक है, so it was like a fan. ठीक है, the fan rotates the blades of the fan about its end. ठीक है, but you must have seen in circus that there are those jugglers and all. ठीक है, they rotate the stick about its center of mass. So there is a difference in the rotational motion. ठीक है, there is a difference in the rotational motion of the same rod. ठीक है, even if you keep there is nothing before this. I have just started it from here only, है ना? ठीक है. So there is a difference in rotation. ठीक है, there is a difference in the way the stick rotates. ठीक है. So if you rotate the stick from the center of mass, it will have a different kind of rotation. If you rotate the stick at its end, there will be a different kind of motion. ठीक है. So the mass is same, the length is same. ठीक है, but the rotational motion is different. ठीक है, the rotational motion has some difference. So that difference is denoted by moment of inertia. That difference can be seen in moment of inertia. ठीक है. So here what we need to find the ICM, moment of inertia about the center of mass. This is called as moment of inertia. Moment of inertia about center of mass. ठीक है, this is called as the moment of inertia about center of mass. ठीक है, the mass of the rod is m, the total length of the rod is l. ठीक है, it is m and l. Mass is m, length is l, and the axis is passing through the center of mass. That means this rod is at a distance of l by 2 from one of the edges. ठीक है, it is at a distance of l by 2 from one of the edges. Now we know that if we want to calculate the moment of inertia, ठीक है, if we have to calculate the moment of inertia for a continuous rod, ठीक है, so it is given as ICM is equals to integral r square dm. ठीक है, integral r square dm, and we know this, we did this in the previous example also. ठीक है, but now what we will do, ठीक है, we have to find the dm and all again. ठीक है, dm, you know, dm is still the same. ठीक है, m by l dx only. ठीक है, in the previous question we have done this. ठीक है, dm we have calculated as m by l dx, है ना. ठीक है, गुड मॉर्निंग. ठीक है, चलो, है ना. So in the previous question we had calculated dm is equals to m by l dx, है ना. So I will directly use it over here. ठीक है, we won't waste time on that calculation again. It is the same. ठीक है, it is the same, there is no difference in that. But what is the difference over here is, first of all, when I draw the x and y axis, ठीक है, x and y axis, earlier my rod was starting from origin. ठीक है, in the previous question my rod was starting from origin. Here my rod is starting from a distance behind, l by 2 distance behind. That means it is starting from x equal to minus l by 2, x equal to 0 I have my axis, and x equal to l by 2 is the right end. Okay, so my rod is shifted like this. Okay, my rod has been shifted behind. Now again, if you see, at a distance of x, okay, I will take a small element, okay, elemental mass dm, okay, whose mass we already know, it is m by l dx, and the length of this elemental mass is dx. Okay, we already know this. And now, so what we will do, we will integrate it. Okay, ICM will be integration of r square. R in this case is what? From the origin, what is the distance of the mass? It is x. So it is x square dm. It is x square dm. So dm, again we can replace this over here. So this will be integration x square into m by l dx. Okay, this will be x square into m by l dx. So you will get m by l integration x square dx. Acha, now let's talk about the limits. Okay, the only difference which is created over here is the limits. Okay, in the previous calculation also we had the same integration, but the limits were different. It were from 0 to l. Now see, your x is starting from minus l by 2 and ending at plus l by 2. Okay, your x is starting from minus l by 2 and ending at plus l by 2. So the limits will now become minus l by 2 to plus l by 2. This will be the integration. This is the integration that we require, that we need. Okay, so again, m by l is the constant, it is outside. So integration of x square is x cube by 3. But now the limits are minus l by 2 to l by 2. Okay, now replace the upper limit. Replace the upper limit. So it will be l by 2 whole cube by 3 minus minus the lower limit, that is minus L by 2 whole cube by 3. Okay, upper limit minus lower limit. Okay, you can see here 3 is coming out to be common, so let's take it out. This will become L cube by 8 plus L cube by 8. Okay, L cube by 8 plus L cube by 8. So this will become m by 3L into 2L cube by 8. That is this. So if you simplify it, you can see here it is coming out to be ml square by 12. It is coming out to be ml square by 12. So therefore, if you change the axis, you can see the value, the result has changed. The result has varied. The result has changed. Okay. So as we can see here,
Zuma.
yeah. Nah. Okay, so as you can see here, as and when I changed the axis just by a distance of L by 2 also, okay, even if I change the axis by a distance of L by 2, still the moment of inertia changed by a lot. Okay, you can see the moment of inertia earlier which you had calculated, it was ml square by 3, I guess. Okay, as far as I remember. So whatever it may be, okay, not a issue for us now. But now it is ml square by 12. Okay, it is ml square by 12. So it has changed. It has changed. So now it is not possible कि I can remember the moment of inertia of the same rod about infinite axis. Okay, there will be many axes, and one axis will be there at a distance of L by 4, another will be at a distance of 3L by 4, and so on. Okay, there are many different axes. Okay, but we need to remember. Okay, you have to, so since there are many axes, okay, there is a standard axis. Okay, there is always a one axis which is always passing through the center of mass. Okay, there is only one axis which passes through the center of mass. Okay, so what you have to do is just remember the moment of inertia about the center of mass. Okay, mute your mic.
Napoli. Klase na.
Somebody's mic is
Sorry.
mic. Mute your mic. ठीक है. अच्छा. So where was I? हाँ. That moment of inertia, ठीक है. There will be again many. There is a list of moment of inertia which you have to remember. ठीक है. But those moments of inertia, if you observe, they all are about the center of mass axis only. ठीक है. So all you have to do is remember the moment of inertia of different shapes about their center of masses. ठीक है. How to calculate about the different axes, ठीक है, we will discuss that later on. ठीक है, we will discuss that also, don't worry. But first you need to remember the moment of inertia of the basic shapes like sphere is there, disk is there, ठीक है, cylinder is there. ठीक है, all of these objects you need to remember the moment of inertia. So I will start writing those moment of inertias. ठीक है, you take a list. ठीक है, make a list, है ना, and you have to remember those values. ठीक है, those are all moments of inertia about the center of mass, है ना, and you have to remember those. ठीक है, so there are two lists which you have to remember. ठीक है, in this chapter, one is the center of mass list and the other is the moment of inertia list. ठीक है, because every time in exams you won't be keep on calculating the integration again and again. ठीक है, that will be like forever, and you will only solve 2-3 questions and come, so that is not beneficial for us. Okay, so better to remember the moment of inertia about the center of masses. Okay, so I will write the moment of inertia which the basic moment of inertias, okay, about the center of masses which you have to remember. Okay, I hope everybody has written this. Okay, you can take a okay. Let's write here shape and ICM. ठीक है, ICM I'm writing. ICM means moment of inertia about the center of mass. Okay, so I will draw the shape only. Okay, I will draw the shape, in fact, instead of writing it, so you can better remember it. Okay, first is your ring. Okay, rod we have already calculated. So let's write rod first. Okay, rod we have already just now calculated. Okay, this is the center of mass. If it is rotating about this, then ICM will be ml square by 12. Okay, we have just calculated this. Acha. Second is your ring. Okay, remember this is the ring. Its radius is r and mass is m. Okay, here its length was L and mass was m. So that is ml square by 12. Here the mass is m, ring radius is r. Okay, so am I audible to everybody? Somehow I got removed from the class. ठीक है है ना ठीक है now back to the moment of inertia thing ठीक है so ring is there ठीक है ring is there so moment of inertia of the ring about its center of mass ठीक है we have already calculated the center of mass will be mr square. This is the value of moment of inertia about its center of mass. We have to remember these values. Okay, it is easy to remember. Okay, some of it are bit tricky, but okay, you can remember those. Then third is
Sir,
ठीक है. Is everything visible now?
No, sir.
No, sir.
Nothing
No,
is
sir.
visible.
No, sir.
अच्छा. Let's see. Yes, now is it visible?
Yes, sir. So could you please scroll up?
Yes, nothing. I have not written anything much, but I don't know what is the issue over here, but still. ठीक है. Let's see. Acha. So now, for second one, I told you that we have the moment of inertia of a ring about its.
Screen is not visible, sir.
Yes. Yes. What you said, I could not.
The screen is not visible.
Screen is not visible.
It's visible, sir. So it's
Sir,
visible.
Some of you are saying it's visible. Some of you are saying it's not visible.
I will try and rejoin.
How many of you are not able to see the screen? Just write it in the chats. नहीं ठीक है. Only you are not able to see the screen. ठीक है. Most of almost everybody else is able to see the screen then. ठीक
I
है.
will
So
try and rejoin.
again rejoin the class. ठीक है. Most probably it should
Okay.
help. And it is visible to everybody else. ठीक है. Must be network issue with him. ठीक है. No problem. ठीक है. Let's see. है ना. So where was I? Moment of inertia. ठीक है. We are trying to write the different moment of inertia of different shapes about their center of masses. ठीक है. So in the second one, if you see, the axis here, if you write the axis is perpendicular to plane of ring. ठीक है. Is passing through the center of mass, no doubt. ठीक है. The axis is passing through the center of mass, but the axis is also perpendicular to the plane of the ring. ठीक है. The ring is in perpendicular direction. You can imagine that if you see a cycle, ठीक है, cycle wheel, ठीक है, and if you insert a rod in between it, ठीक है, through its center, so that axis is this axis, ठीक है, which we are talking about, है ना. In this third one, in the third diagram which I have drawn, ठीक है, the axis is here, the axis is in the plane of ring. ठीक है. Here the axis is in the plane of the ring and still passing through the center of mass. ठीक है. It is still passing through the center of mass, but it is in the plane of the ring. ठीक है. It is in the plane of the ring, or you can say it is along the diameter of the rod. ठीक है. You can say that this distance is how much? It is the diameter of the rod, of the ring, and through that diameter only the axis is also passing. ठीक है. Through that diameter only the axis is also passing. So these are the two ways. These are the two ways in which you can pass an axis through the center of mass in a disk. ठीक है. In a disk you can pass the axis through center of mass in two ways. That is the second and the third one. ठीक है. You just have to remember these. ठीक है. All of these calculations, and all of these calculations were done by integration only. ठीक है. They were done by integration. They were derived by integration. We are just remembering the result. Okay, we don't have to go into integration and all, just not okay, we don't have to worry about it that much. Okay, you have to just remember the results, because that is the thing which we are going to use further. No one is going to ask us the derivation, so we don't have to worry about it. Okay. Fourth is your disk. Okay, this is a disk. Mass is m and radius is r. So again, you can see the axis is perpendicular to the plane of the disk. Okay, axis is perpendicular to the plane of the disk. है So if you want, you can write here axis is perpendicular to plane of disk. So in this case, the moment of inertia comes out to be mr square by 2 for the rod, for the disk. Okay, the disk has a moment of inertia of mr square by 2. Next is the
So
same.
how is this
Yes.
different from ring?
What?
How is disc different from ring?
Acha. In ring, you have only mass on the outside. Okay, it is like a shell. It is only mass over here. Okay, but in disk, mass is everywhere. This complete is mass. Okay,
Okay.
so it is like CD and your ring. Okay, CD is disk, but ring is ring. Okay, you must have seen a ring. Okay, I cannot
Yes.
describe it in any other way. Okay, or you can say that cycle wheel is a ring. Okay, and CD is a disk. Okay, that is the best explanation. Okay, best example you can say.
Excuse me, sir.
Yes.
But how both of them have the same formula?
Formula can be same. Why not? On integrating, okay, first of all, the formula is not same. Okay, if you see, the ring is rotating about an axis in the plane of the ring. Okay, it is rotating about an axis in the along its diameter. Then its moment of inertia is mr square by 2. If you keep the axis same, okay, if you keep the axis same, and if you see the ring and the disk, there is a difference of moment of inertia. Yes. If the axis is perpendicular, then the ring has mr square moment of inertia, but the disk has mr square by 2 moment of inertia. So there is a difference. There is a difference. It is not same. है
Okay, sir, understood.
ना? So see, you might feel कि sir many of the formulas are repeating. ठीक है, you might say sir कि इसका भी mr square by 2 है, इसका भी mr square by 2 है, but it is not like that. ठीक है, these things are derived from integration. ठीक है, so there is a possibility that formulas may match. ठीक है, integration is just a mathematical tool. ठीक है, it is not necessary कि every time it will give something new only. ठीक है, so after integration these are the results, so we cannot just interfere with it. है ना, if these are the formulas, these are the formulas, you have to remember it. It is like center of mass. ठीक है, on integration I got the values of center of mass, so I have to remember them. ठीक है, I cannot just go and interfere with the center of mass. It is not on me to say that the center of mass should be somewhere here. ठीक है, its distance should be something else. I cannot say I cannot do anything about it. And if it is coming equal, it is coming equal. Okay, we cannot just change it. Okay, so these are the results you have to remember. Okay, just it is a small table. Okay, around 9-10 shapes are there. Okay, just remember those. Okay, as and when you practice na. Okay, the more you do questions, the more it will be easier to remember those things. Okay, so you will get used to it. Don't worry. Okay, it is just the starting, so it is looking sir how 10 things we have to remember. So that is a issue. I know that. Okay, it happens, but slowly and slowly as you do questions, okay, it gets you get used to it. Okay, so that is, don't worry about that. Okay, just try to do more questions. you will start remembering the moments of inertia. ठीक है. अच्छा. So next is that if I have a disk, but now my axis is passing through the diameter, same as a ring only. ठीक है. Center of mass is here only, but now it is passing through the ring diameter. ठीक है. This is disk, mass is m, radius is r, and axis is in the plane of disk. Okay, so for this axis, the moment of inertia comes out to be mr square by 4. Okay, it comes out to be mr square by 4. We have to remember it. Okay, there is not an issue in that. Next is 6th. This is a hollow cylinder. Okay, this is a hollow cylinder, and the axis is passing through and through like this. Okay, let's draw it, no problem. Okay, axis is passing through the axis of the cylinder only. Okay, if the rotational axis is through the axis of the cylinder, its mass is m, radius is r. It is a hollow cylinder. Hollow cylinder means it is something like a tube. Okay, in tube you know that there is a free space in the between. Okay, only a covering is there. Okay, shelling is there. So it is a hollow cylindrical shell, you can say. Okay, so if it is a hollow cylindrical shell, then the moment of inertia comes out to be mr square. Okay, the integration is mr square. And if it is a if it is a solid cylinder, okay, if it is a solid cylinder, okay, everything is filled, then it comes out to be, okay, mass is m, radius is r, this is the axis, this is a solid cylinder. Moment of inertia comes out to be mr square by 2. Okay, mr square by 2. So you can see that it is a bit easier to remember. Okay, how? Okay, just try to create a cylinder. Okay, cylinder can be created by keeping one ring above the other. है ना? A hollow cylinder, a combination of rings. Okay, you can say infinite number of rings were used to create a hollow cylinder. So just see the moment of inertia of the ring about its axis perpendicular is mr square, and also of the hollow cylinder is also mr square. So ring and the hollow cylinder both have same moment of inertia. Okay, both have same moment of inertia. So mr square and mr square will be the moment of inertias for both. Okay, similarly for disk, if you see the disk, okay, for the disk it is mr square by 2. Okay, for an axis passing through the center. And if you stack one disk over the other, okay, if you stack one disk over the other, it will become a cylinder, solid cylinder. So solid cylinder's moment of inertia is how much? It is the same as disk. Okay, so it is easier to remember. Okay, if you don't even remember the hollow cylinder and solid cylinder, okay, directly from ring and disk, we can calculate the moment of inertia. Okay, so this simplifies your, terms. Okay, this reduces your terms, in fact. Okay, so two terms are directly reduced. Okay, you don't have to remember hollow cylinder and solid cylinder. Okay, directly you can remember that hollow cylinder is same as ring and solid cylinder is same as disk. Okay. Acha, let's move further. 8th is your solid sphere. Okay, it is a sphere now. It is 3D object. Okay, it is solid sphere. Okay, this is the center of mass, and an axis, any axis, okay, passing through the diameter will be a.
Excuse me, sir.
Yes.
Could you please show hollow cylinder part?
Yes. Yes.
Yes, sir. Thank you.
ठीक है. So in a solid sphere, ठीक है, you can imagine that any line passing through the center of mass, ठीक है, will be equal. ठीक है, why it will be equal? Because it is dividing the whole sphere into two hemispheres, equal hemispheres. Anywhere the line passes, ठीक है, it doesn't matter. So the moment of inertia about this axis, ठीक, it always comes out to be 2 mr square by 5. ठीक है, it is remembered at 2 as 2 by 5 mr square. ठीक है, it is easier to remember. 2 by 5 is the coefficient of, you can say, solid sphere. ठीक है, mass is m, radius is r. This is standard. ठीक है, and if we have a hollow sphere, ठीक है, if there is a hollow sphere, that is a shell, hollow sphere or a shell. ठीक है, again this is the center of mass. So if I draw an axis passing through it and it is rotating about this, mass is m, radius is r. So for a solid hollow hemisphere, it will come out to be 2 by 3 mr square. 2 by 3 mr square. ठीक है, so these are some of the shapes of which moment of inertia you have to remember. ठीक है, because questions most probably will be asked from them only. ठीक है, if the axis changes, what we have to do, we will see this later on. ठीक है, just after this we will see. We will first do a few questions, then we will see. ठीक है, so write this. Anybody if wants to, if I wants the other 4, other 5. ठीक है, so I can scroll up, no problem in that.
So for triangle, it will be same of disc, right? I mean cone.
Cone. ठीक है, don't worry. ठीक है, we don't the moment of inertia of cone is not in our scope. ठीक है, but you can say that it should be 1/3 of your cylinder. ठीक है, it should be 1/3 of your cylinder. ठीक है, we have to calculate it. ठीक है, I am just saying as an estimate. ठीक है, it is not an exact answer. ठीक है, because cone is not a very popular shape to be used in rotational motion.
Okay, sir.
ठीक है, so questions don't come on cone. ठीक है, that is why they are not standard. ठीक है, they are called as they are not in the standard table. ठीक है, but if you want, we can derive that. ठीक है, we have to do a derivation for that, then only can we comment on it. ठीक है, before that I cannot say anything. ठीक है, ठीक है, so I guess everybody has written this. ठीक है, if anybody wants, you can see this also, the first 5. ठीक है, I guess everybody has written this. है ना, so this table you have to remember. ठीक है, these are the standard shapes. ठीक है, these are the standard shapes and most of the questions will be asked on these standard shapes only. ठीक है, if some unknown shape arrives, ठीक है, if unknown shape is asked, you can integrate it. ठीक है, but they won't ask. ठीक है, you don't have so much time to calculate for new shapes. These are standard shapes. At least this much you have to remember. ठीक है, these 9 should be definitely remembered. है ना, ठीक है, next is, Okay, let's see a question. Okay, let's see a question. Let's suppose okay, I have a rod. Okay, I have a rod of length L. I have a rod of length L and mass is M. And at the ends, okay, at the ends of the rod, okay, at the ends of the rod, small m masses are connected. Okay, they are connected at the ends of the rod, and the rod is being rotated about its center of mass. Okay, in most of the cases, uh, questions will be written in word format only. Okay, you can convert it in diagram. Okay, that in that way you will be able to understand. So that is easy. Okay, you can do that. Everybody of you know English. Okay, I know that. So you can easily draw the diagram from the given question. Okay, so I am directly drawing the diagram just to save time. Okay, acha. Now see what they are asking is what is the moment of inertia of this system about its center of mass. Okay, what is the moment of inertia of the system about the center of mass of the rod. Okay, so simple, it is very simple. Okay, first of all, moment of inertia is a scalar quantity. Okay, so there is no vector thing. So once you have the values, just add them up. Okay, just you have to add them up. Now see this mass. Okay, this is a point mass. Okay, and this is also a point mass. The 2 point masses are at a distance of L by 2 and L by 2 from the axis of rotation. Okay, they are at a distance of L by 2 and L by 2 from the axis of rotation. So if such a thing is happening, so it is simple. Just remember that moment of inertia of the system will be what? Moment of inertia of the system will be moment of inertia of rod plus moment of inertia of small m mass plus moment of inertia of small m mass, because there are two small m masses. Okay, there are 2 point masses connected at the end. Acha. First of all, let's talk about moment of inertia of the rod. Okay, what will be the moment of inertia of the rod about this axis? Okay, this a dash axis. This axis is passing through the center of mass of the rod. Hence, its moment of inertia will be ml square by 12. We have just written the list. Okay, so you have to remember it. So moment of inertia of the rod is done. What about the moment of inertia of the point masses? Okay, moment of inertia of point mass is written as directly mr square. Okay, it is directly written as mr square. So mass is small m, and the distance r is what? It is the distance of the point mass from the axis. Okay, so in this case, the r will be L by 2 whole square. L by 2 whole square. Okay, this is for one of the point mass. The other point mass, if you see, the other point mass also has the same moment of inertia. It also has the same moment of inertia. Okay,
Excuse
so
me,
if
sir.
it is, yes,
Sir, can you explain again how you got the M value?
the moment of the rod,
No, sir. Of the mass.
point mass. See, for the point mass, if you are writing, just concentrate on the point mass. Okay, just concentrate, forget everything else. Okay, what is the system you are having? It is this, that you have point mass small m. This is the axis a dash, and it is at a distance of L by 2. That's it. Okay, forget that there is another rod and there is another mass. Okay, if you are just concentrating on this mass, what you write the moment of inertia for point mass? We have already seen the formula as mr square. That's it. Okay, for the point mass, I have written that in the first, starting of the moment of inertia. So it is directly mr square. So what is m? M is the mass of the object. So that is small m only. Okay, no change in that. But what is r? R is the distance of the point mass. Distance of the point mass from the axis. Okay, so distance of the point mass from the axis is how much? It is L by 2. So it is L by 2 whole square. So that is why I have written it directly here, m L by 2 whole square.
Okay, got it, sir. Thank you.
Okay. Yeah. है ना. So this is how you can calculate moment of inertia. ठीक है. अच्छा. Now I cannot help in that. ठीक है. Just go with Geo. ठीक है. Try to get a Geo network, Geo fiber, and it will help. ठीक है. So I cannot help there. ठीक है. चलो. So the net moment of inertia, you can calculate it. After this, it is simple calculation. ठीक है. These two terms will get added. ठीक है. That will be 2 times m into L by 2 whole square, that is L square by 4. So this becomes ml square by 12 plus ml square by 2. ठीक है. So if you want, you can simplify it further, but let it be. This is the moment of inertia of the system about its center of mass. ठीक है. About its center of mass. Okay, so this is how we calculate moment of inertia for different point masses and combination of it with the center with continuous objects. Okay, if the axis is passing through the center of mass, remember always that. Okay, acha. Let's see another variation. Okay, let's see another variation. This is the axis of rotation. This is the center of mass, but now the rod is at an angle of theta with the rod. ठीक है. It is rotating like this, so you can imagine the rod will be rotating at angle. ठीक है. It will be trying to make a cone. ठीक है. Something like this, not this color. Let's change it. ठीक है. It will be rotating something like this, and it will be trying to make a cone like this. ठीक है. Cone will be made over there. So if it is rotating like this, then what is the moment of inertia of the system we have to calculate? And what is the moment of ठीक है. What is ICM in this situation? ठीक है. Because still the axis is passing through the center of mass only, so I cannot say it something different. ठीक है. It is still passing through the center of mass, so it is still the moment of inertia about the center of mass of the rod. ठीक है. So I cannot do anything about that, but we can calculate how. Let's see. The mass is m, length is l. ठीक है. We don't have to worry about it. Mass is m, length is l. है ना. What we can say is that earlier, ठीक है, when the rod was like this, ठीक है, the moment of inertia in this case came out to be ml square by 12. ml square by 12. ठीक है. This we know. ठीक है. This we know. Now see, if this length is at an angle of theta with the perpendicular with the axis, so can we say that with respect to this L, this new length, okay, with respect to this capital L, that is the new length, okay, let's write this as small l, है ना. This is the length of small l. Okay, let's see. Let me just draw it like this. Okay, this length is capital L, है ना, and this length comes out to be small l. This length comes out to be small l, and if you see the angle between these two, if you see the angle between capital L and small l, okay, that comes out to be 90 minus theta. Okay, that is coming out to be 90 minus theta, because you can see that it is at 90 degrees, so 90 minus theta will be the remaining angle if that is the angle theta. So here you can say that this angle is how much? It is 90 minus theta. Okay, so if you drop a perpendicular over here, what we can write? We can write cos of 90 minus theta. Cos of 90 minus theta is equals to L by capital L. Okay, you can replace cos of 90 minus theta as L by capital L. So L comes out to be, small l comes out to be capital L sine theta. Cos of 90 minus theta is sine theta. ठीक है, everybody knows that. ठीक है, you must have done it many a times. So what we can say is that the moment of inertia of this component, ठीक है, you can say this element, this part will be m L sin theta whole square by 12. m L sin theta whole square by 12. ठीक है, so this comes out to be m L square sin square theta by 12. ठीक है, this is the moment of inertia of this component, है ना. If you see there will be another component which is in this direction, ठीक है, which is in the perpendicular direction, that is it is along the axis. ठीक है, it is along the axis. Now just imagine that you are holding your pen in vertical direction. You are holding your pen in vertical direction and rotating it about its vertical axis only. ठीक है, so literally you can see that there is no rotational motion. ठीक है, your pen is rotating because it has some width. ठीक है, it is having some width, so you can see some rotation motion. ठीक है, there is something drawn on it or something is there. But just imagine that it was a simple plain rod. It is a steel rod. ठीक है, you won't be able to tell that the rod is rotating. ठीक है, you won't be able to tell that the rod is rotating about this axis. ठीक है, so moment of inertia of this component is zero. Moment of inertia of the vertical component is zero, but the horizontal component is coming out to be ml square sin square theta by 12. ठीक है, it is coming out to be ml square sin square theta by 12. Therefore for the rod, ठीक है, which is at an angle theta like this, ठीक है, for a rod which is at an angle theta from the axis, but axis is passing through center of mass, ठीक है, the net moment of inertia about this axis becomes ml square sin square theta by 12 plus 0. ठीक है, it should be plus 0, but plus 0 has no meaning, so I am leaving it. ठीक है, is it understood? Yes.
So please scroll up.
Yeah. है ना, I have done nothing. I have just taken the components, you can say. ठीक है, I have taken the components of length here. ठीक है, I have taken the components of the rod. ठीक है, the rod has two components. One component is perpendicular to the axis and the other component is vertical along the axis. ठीक है, so if it is like this, ठीक है, the components are these two components are there, then I can say that the sum of these two components will be the net moment of inertia. ठीक है, previous question. अच्छा, you want the previous question? Yes. ठीक है, so these are the few variations which can be created. ठीक है, so just keep these in mind. ठीक है, these are the variations which can be created, so you have to keep this in mind. अच्छा, so write this first, then we will move on to the part where if the axis changes, what we can do. ठीक है, how to inculcate that change of axis. Done. ठीक है, and if you want you can write this also. ठीक है, so now we will see that what happens. ठीक है, how to calculate if the axis is not the axis of center of mass. ठीक है, we have to see that how the moment of inertias vary. ठीक है, how to calculate moment of inertia in such situations. ठीक है, so we will see that. ठीक है, so I guess everybody has written this, है ना? अच्छा, so to so if we have to calculate moment of inertia about some different axis, ठीक है?
Excuse me, sir.
Yes, scroll down.
So I got disconnected for the last 5 minutes. Can you explain this problem again?
Again, we have to do this problem. The blue one or the red one?
No, sir, the blue one.
ठीक है, ठीक है, ठीक है. So see, in this problem, ठीक है, we had to calculate the moment of inertia about a rod which is at an angle theta from the axis of rotation, that is AA dash. ठीक है. So what we did is that we broke it down into two components. One is the perpendicular component, one is the parallel component. ठीक है, one is the perpendicular, other is the parallel component. The perpendicular component, ठीक है, when I started calculating the moment of inertia for the perpendicular component, it came out to be ml square sine square theta by 12. ठीक है, how? Let's see. First of all, what we did, this was the length L. ठीक है, this at this angle there was a length L rod kept like this. ठीक है. What I needed was the horizontal component of this length, that is this small L I needed. ठीक है, because about that rod the moment of inertia is ml square by 12. I know that. ठीक है. I just need to find the length of that component of rod. ठीक है. So what I did is I drew a right angle triangle. ठीक है. The capital L length was the hypotenuse and small l length was the component which I require. ठीक है. The angle between these two, when I calculated, it came out to be 90 minus theta. ठीक है. It came out to be 90 minus theta. So what I did is I wrote cos of 90 minus theta. So that came out to be small l by capital L. So from here, small l came out to be L sine theta. Now what I did, I replaced the small l sine theta over small l value over here. Okay, as and when I replaced it, I got the moment of inertia of the rod perpendicular to the axis of rotation. Okay, that is ml square sine square theta by 12. है ना? The other component, that is the vertical component, that is the parallel component, you can say. ठीक है, the parallel component's moment of inertia was coming out to be 0. Why? Because when I rotate a rod about its parallel axis, ठीक है, about an axis parallel to the axis of the rod, ठीक है, there is no rotational motion visible. ठीक है, there is no rotational motion visible. It is, see, even when I am drawing it like this, ideal rod does not have this much width also. Okay, that width is just for our reference. Okay, this much width is a very large width for a rod. A rod is just a straight line. Okay, it is like this only, ideal rod. Okay, so if you rotate a straight line, okay, you can't see any effect. Okay, if you rotate it about its own axis, okay, if you rotate it about this axis only, okay, you won't be able to tell any difference between the rotation. Okay, so that is why the moment of inertia about that axis came out to be 0. And so moment of inertia about this axis is 0, and moment of inertia of the perpendicular rod is this much. So the net moment of inertia is the sum of these two, that is ml square by sine square theta by 12. So that is the moment of inertia which we need.
Sir, can you scroll up to the red one, because I will take a screenshot.
Okay, no problem. ठीक है.
Thank you, sir.
Yeah. ठीक है, I guess I got this, है ना?
Yes, sir. Got it, sir.
ठीक है. So now let's move on to the changing of axis. ठीक है. So axis change, ठीक है, can be calculated. ठीक है, if there is a change of axis and we want to calculate moment of inertia, that is coordinated, or you can say can be calculated using two theorems. Okay, there are two theorems on moment of inertia. Okay, there are two theorems on moment of inertia, okay, which determine what should happen if the axis is changing. Okay, first theorem is theorem of parallel axis. Okay, first is the theorem of parallel axis. So what happens in this case? What happens in this case is, suppose I have a body. Okay, suppose it is a 3D body. Okay, like this. It is kept in XZ plane. And suppose its center of, this is the center of mass, and about this axis, okay, about this axis, if you calculate the center of mass, okay, it will come out to be ICM, no doubt in that. Okay, but suppose I need moment of inertia about some different axis. What is that axis? Suppose that axis is somewhere over here. Okay, suppose that axis is somewhere over here. Okay, suppose it is at some distance a. Okay, it is at some distance a. Now if we calculate the moment of inertia about this new axis, okay, let it be a dash. Okay, this was CM, ICM, we can write it directly, axis about center of mass, so we don't need to define it. But if you need the moment of inertia about the new axis, I, okay, let the moment of inertia about the new axis be I. So moment of inertia about the new axis can be written as ICM plus MA square. ICM plus MA square. Okay, so this is how we can write moment of inertia about the new axis. This is a theorem. Okay, this is a theorem of parallel axis. Okay, so I guess it is clear. Okay, we will see questions. And how to deal with it. है But first before that, let's see the what is the terms. Okay, what are the important terms which you have to take care while using this axis, while using this theorem? Sorry. Okay, first of all, the first term is the mass. Okay, this m is the total mass of object. Okay, it is the total mass of the object. It is not a part of the mass. Okay, it is not an elemental mass. It is not dm. It is the total mass of the object. Okay, and what is a? You have to be careful. A is the perpendicular distance. It is the perpendicular distance between a dash and center of mass axis. Okay, so first of all, for this theorem to be applicable, you need two parallel axes. A dash and center of mass axis are parallel to each other. Okay, don't write parallel like this, you will break your habit. Parallel to each other. Okay, a dash and center of mass axis are parallel to each other. Then only this theorem is applicable. Okay, if they are parallel to each other, then the perpendicular distance between these two axes, parallel axes is a, and hence I can apply this formula. Okay, so these are the few points which you have to take care about. And these are the few relations, few important things which you have to take care before applying this formula. Before applying this theorem. अच्छा Any doubts, anybody in this? I guess it is clear. है ना? Acha, let's say that suppose you have to find you have to derive this. Okay, if you want to derive this, it is derivable. Okay, not an issue. Okay, but it is not important, but still we will do this. Okay, let's see. Suppose I have taken a small mass m1 on the object. Okay, small mass m1 of the on the object. Okay, its distance from the center of mass is r, and the separation of these two is a. Okay, this is the situation that is happening. So let's name this as point P. Okay, let's name this as point P. So if you want to calculate the moment of inertia of the center of mass about point P, okay, moment of inertia of the center of mass about point P, you can say that it is m1 r square. Okay, it is m1 r square. And now see, if we, this was for 1 point mass, this was for 1 point mass. Okay, the complete capital M mass, the complete capital M mass is what? It is combination of infinite point masses. Okay, it is combination of infinite point masses. So you can write this as summation of m r square. Okay, it is the summation of infinite point masses. Okay, let's keep it at summation only. Okay, we don't go towards integration. It just confuse nothing else. So let it be summation only. Both are having the same meaning. Okay, just keeping summation is the bit you are relatable to it. So let's keep it on summation. Okay, no need to go to integration. Acha. Now, if we want to write the moment of inertia about a dash of the point P, okay, if we want to write the moment of inertia about a dash axis, okay, so you know that to write the moment of inertia for point object from one of the axis, you need this total distance. Okay, you need the total distance from that axis. Okay, the distance from moment of center of mass was r, so I used mr square. But when I changed the axis, my distance also changed. Okay, how much is that distance now? You can see that it is r plus a. It is r plus a. Okay, from the a dash axis, my point mass is at a distance of r plus a distance. Okay, so moment of inertia will become what? m1 r plus a whole square. R plus a whole square. So in the similar manner, if you want to find the moment of inertia of the whole this object.
Scroll up.
Yeah. Okay. Suppose now, if you want to calculate the moment of inertia of the whole object, then what we can do? We can just apply summation. That's it. Okay. Summation m of r plus a whole square. Okay. Summation
Yes,
r
sir,
plus
done.
a whole square. Okay. Acha, now see. R is a variable, A is a constant. Remember this. Okay, the distance between the two axes is constant. Okay, it is not varying. Okay, R is varying. Sometimes the point mass will be here somewhere. Sometimes the point mass will be here, and it will keep on varying. Okay, that is a different matter. But for now, okay, you can see that R is a variable, A is a constant. Okay, so what I can write? I can write that a dash at point P is summation of m r square plus a square plus 2ra. R square plus a square plus 2ra. ठीक है. अच्छा. Now see, the moment of inertia about this axis is written as I. ठीक है, moment of inertia about this axis is written as I. Okay, I have assumed it to be I. And this can be written as summation mr square plus summation ma square plus summation m2ra. ठीक है, I have divided the summation in the three terms. ठीक है, now see, this summation mr square, this summation mr square is what? This summation mr square is basically your ICM. It is basically ICM. ठीक है, so this comes out to be I is equals to ICM plus summation ma square. If you see, m is also constant, a is also constant, so the summation of ma square will become capital M A square. Okay, it will a square is a constant, so it will come out. There will be summation of small m. Summation of small m means what? Collection of all the point masses which is constituting the big object. It is constituting the large object. So summation of small m becomes capital M. Okay, it is simple. It is understandable, I guess. Okay. And lastly, in the third term, 2a is constant, so 2a will come out. Summation of mr will be there. Summation of mr will be there. Now see. If you see, this is the center of mass. Okay, we have seen that whenever we are trying to calculate this, the moment of inertia, always the center of mass is kept at origin. Okay, always the center of mass is kept at origin. Okay, so if center of mass is kept at origin, so I can say that xcm is what? Xcm is 0. Okay, or you can say just rcm is 0. Instead of xcm, let's write it as rcm equal to 0. Okay, why rcm is 0? Because my center of mass is at origin. Okay, center of mass is at origin. So if my center of mass is at origin, you can write the formula summation mr upon summation m is equal to 0. Okay, so you can say from here that summation mr is what? Summation mr is 0. Okay, summation mr is 0. This is extra. Okay, you can say this is just a part used in derivation. Okay, so since this summation mr is becoming 0, this term is becoming 0, the net result which I am left is with ICM plus MA square. This is the parallel axis theorem. This is the parallel axis theorem. Okay, so this is the derivation. This is a small derivation of the parallel axis theorem. Okay, I don't think it is of much importance anywhere. Okay, it is not used very widely. Okay, derivation, sorry, derivation is not asked many places at many places. Okay, but the application is important. Okay, the application is important. Okay, so we will see the application. We will see the application. Okay, so write this first. Any doubts? Anybody? Anywhere? Very simple thing. Okay, it is a basic thing. Okay, it is not a very complicated thing. Okay. Guess everybody has written. Now let's see the second theorem. Okay, there are two theorems which you have to know. Okay, second theorem is theorem of perpendicular axis. Okay, second is the theorem of perpendicular axis. Okay, what is the theorem of perpendicular axis? That suppose again I have a object. Okay, I have some object. Okay, one axis is x. Okay, passing through the center of mass. Another axis is y, passing through the center of mass again, and the third axis is z, which is in the z direction. Okay, all are passing through the same point, that is the center of mass. Okay, so if such a situation is happening, and just imagine, let's take it that the moment of inertia about x is known to me, the moment of inertia of y is known to me, but I need to find the moment of inertia about z. I need to find the moment of inertia about z. Okay, so as per theorem of perpendicular axis, what I can write is that moment of inertia about z, is moment of inertia about x plus moment of inertia about y. Simple. That's it. Okay, moment of inertia about z is the summation of moment of inertia about x and moment of inertia about y. ठीक है, and it is a very simple thing. ठीक है, so we will see examples
Sir,
on
I
it.
lost connection. Can you just zoom out a little bit?
Yes,
Oh,
yes.
this is the second theorem.
Hmm. ठीक है,
Okay, sir. Thank you.
है ना. So this is the theorem of perpendicular axis. Whenever your axis, है ना, whenever your axes are perpendicular to each other, that is in the direction of x, y and z, ठीक है, then the axis coming out of the plane, ठीक है, x and y are in the plane and z is coming out of xy, ठीक है. So the moment of inertia about that plane is the summation of the other two, ठीक है, is the summation of the other two, ठीक है. So we can see that in an example, ठीक है, like suppose for example, ठीक है, you had your disk, ठीक है, you had a disk, है ना. We have already calculated about the disk, ठीक है, but still let's say, ठीक है, see the moment of inertia about this axis, ठीक है, about this axis, this is z axis suppose, ठीक है, I know the moment of inertia about z axis, how much it was, mr square by 2, ठीक है, it was mr square by 2. But now what I need the moment of inertia about this axis, about the diameter, that is in the x direction, ठीक है. So what you can see here is that z and x are perpendicular to each other, no doubt in that. But for the perpendicular axis to be valid, ठीक है, to be applicable, you need another perpendicular axis like this in the plane of the disk, that is in the y direction. This is y, ठीक है, not this is y, sorry, this is y, ठीक है. So x and y, in the xy plane your disk is there, ठीक है, in xy plane your disk is there, and along a axis perpendicular to the plane you know the moment of inertia, ठीक है, and I want the moment of inertia about x. So first of all, is it visible to you that moment of inertia about x will be equal to moment of
Please
inertia
scroll
about
up a
y?
bit.
Yeah, ठीक है, है ना. So first of all, just see here in the example, ठीक है, that you can see that the moment of inertia about x will be equal to the moment of inertia about y. Why I am saying such a thing? Because it is similar, it is the same, ठीक है, just your disk has been rotated by 90 degrees in the same plane, ठीक है. So it won't create any effect, the rotation will happen as it is, ठीक है. The disk is completely divided in half along the x axis also, along the y axis also, ठीक है. So the way of rotation, you can say, the manner in which it will rotate is same, ठीक है. Along the x also it will be the same, along the y also it will be same, ठीक है. So I can say that the moment of inertia about x and about the y will be same, it will be equal, ठीक है. So I can let it be equal to I, ठीक है. Let's assume that it is equal to I. So as per theorem of perpendicular axis, what I can write that Iz is equals to Ix plus Iy, ठीक है. Iz is equal to Ix plus Iy, simple, because z is perpendicular to x and y, है ना. So Iz is how much? It is mr square by 2. We already knew that from the formula, ठीक है. And Ix and Iy is what? I plus I, that is 2i. So from here you can see that I comes out to be mr square by 4. I comes out to be mr square by 4. If you see the table, this is what the formula was written. Exactly same, mr square by 4 for an axis passing through the diameter, ठीक है. So from here that formula is derived. So another formula is reduced, ठीक है. If you remember the theorem of perpendicular axis, ठीक है, another of the formula is reduced, ठीक है. So write it quickly, ठीक है. There is just one example of theorem of parallel axis remaining, ठीक है. Let's complete that and this topic will be over, ठीक है. So write this quickly, ठीक है. I have not done any question on the theorem of parallel axis, so we will do that also first. ठीक है, so I guess everybody has written this, है ना? ठीक है, so let's see a question, ठीक है, which is basically you can say purely based on theorem of parallel axis. ठीक है, what is
So
that
just show
question?
the previous diagram. Yeah, done, sir. Thank you.
Yeah, ठीक है, so now let's see a question purely based on theorem of parallel axis. ठीक है, so for that you need the basic requirement. There is a basic requirement of the standard moment of inertia, but ठीक है, now just you have written it, so not an issue. You can just see the list and from that list we can take the values. ठीक है, so what is the question that I have? ठीक है, this is the situation that three equal spherical shells, ठीक है, these are all spherical shells, so let's write three equal spherical,
Could you please
not,
scroll up?
yes,
So a little more.
huh, little more,
A little fast connection.
yeah, no problem, no problem.
Yes, so thank you.
ठीक है, so just see question, three identical, ठीक है, instead of equal, identical spherical shells, ठीक है, three identical spherical shells of mass m, of mass capital M are connected like this, ठीक है, are kept like this, ठीक है, touching each other, ठीक है. So what we need here is we need to find the moment of inertia about an axis passing like this, ठीक है, moment of inertia about a dash like this, ठीक है, I might have drawn it a bit tilted, but let it be, ठीक है. So if we want the moment of inertia about this axis, है ना, so what we can do is, first of all, see, all the three have masses m and all the three have radius r, ठीक है, all the three have radius r, ठीक है. So if you see here, let this be c1, this be c2 and this be c3, ठीक है. So these three centers are basically the center of mass of the three spheres, three shells, ठीक है. अच्छा, now if you want to find the net moment of inertia, if you want to find the I net, ठीक है, net moment of inertia of the system, what we can write, I1 plus I2 plus I3. Why? Because it is a scalar quantity, ठीक है. So if you individually calculate the moment of inertia about the given axis, ठीक है, then you just have to add them, ठीक है, you just have to add the values. अच्छा, now let's talk about I3 first, ठीक है, let's talk about I3 first, ठीक है. When I'm talking about I3, I can say that the axis a dash is passing through the center of mass. So moment of inertia of I3 is basically the moment of inertia about its center of mass, simple, ठीक है. And by the formula, by the list, ठीक है, I can say that it is 2 by 3 mr square. You can see that in the formula, you can see that in the formula, ठीक है. It is I is equals to 2 by 3 mr square, ठीक है. It is spherical shell, it is hollow spheres, so the moment of inertia is 2 by 3 mr square, ठीक है. So I3 we know, ठीक है. But what about I1 and I2? What about I1 and I2? Let's talk about I1, ठीक है. Let's take it out separately, just bring out I1, ठीक है. This is I1, ठीक है. This is the axis passing through it, ठीक है. About this axis, this is a dash, this is a dash, and I want to find the moment of inertia of I1 about this axis, ठीक है. But the center of mass is over here, but the center of mass is over here. So if you draw an axis like this, you can see that these two axes are parallel to each other. Okay, you can easily see that these two axes are parallel to each other. And what is the perpendicular distance between them? The perpendicular distance between them is r. The perpendicular distance between them is r. So moment of inertia about a dash. Okay, for the
Not
first
visible.
screen is not visible.
So it is visible.
Okay, so let me just complete the question. Okay, then somebody will take a screenshot and post it in the chat. Okay, so don't worry about it. Okay, somebody will do that, no problem. Okay, so just see here. Moment of inertia about a dash I am talking about. Moment of inertia about a dash. Okay, so moment of inertia about a
It's
dash
visible
using
also.
the acha, okay, so moment of inertia using theorem of parallel axis. Okay, if I can use the theorem of parallel axis, I can write that moment of inertia about a dash, that is the new axis, is equal to moment of inertia of ICM plus MA square. Okay, moment of inertia of a dash is ICM plus. So what is ICM? Here it is a shell. Okay, it is a shell. I have written in the question only that it is identical spherical shell. So it is a shell. So moment of inertia of ICM is 2 by 3 mr square. It is 2 by 3 mr square plus m is the total mass of the shell. Total mass of the shell is capital M. And what is A? A is the separation. It is the distance between the parallel axis. It is the perpendicular distance between the parallel axis. In this case, the perpendicular distance is r. So it is plus mr square. Okay, so if you calculate this, this will be 5 mr square by 3. This is I1, you can say. This is I1. Okay, what about I2? What about I2? If you see, I2 is also identical on the opposite direction. Okay, I2 is identical, but the axis is on the opposite direction. Okay, everything will be same. This is the center of mass. Center of mass is passing here. A dash is this. This separation is R, and this is the center of mass. Okay. So this separation is R. So again, if you apply the theorem of parallel axis, you can again write that IA dash is equal to ICM plus MA square. Again, the same values will be written. That is 2 by 3 MR square plus MR square. Because again, the separation, perpendicular separation is how much? It is R. So again, if you calculate it, it will come out to be 5 MR square by 3. It will come out to be 5 MR square by 3. This is I2. This is I2. So you can see that I1 and I2 are equal because they are identical in scalar. Okay. So therefore, the net moment of inertia will be I1 plus I2 plus I3, that is 5 MR square by 3 plus 5 MR square by 3 plus 2 by 3 mr square. So if you add this, it will be 10 plus 2, 12 mr square by 3. That is 4 mr square. You don't have to remember this. Okay, this is something which can be calculated. This is something which can be derived. Okay. So this is an example of your theorem of parallel axis. Okay, how to apply parallel axis, how to use parallel axis. Okay, so this is it, and your moment of inertia is done. So just write it, solve it. Okay, and then that's it for today. Okay, thank you. If anybody has doubt, can ask.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
So please scroll down.
Scroll down. Achha.
Thank you, sir.
Thank you. ठीक है, so I'm closing it. ठीक है, I'm ending the meeting. I guess everybody has written. ठीक है then. Thank you everybody.